This presentation discusses the development of a possible lunar orbiting refueling system. One of the major challenges faced by the current space industry is the incredibly high cost of deep space and interplanetary operations. A main reason for this is, in addition to all the fuel and resources needed to transport the vehicle itself from the Earth's surface into space, all the fuel required to deliver that vehicle from Earth orbit to deep space is also needed to be brought from the Earth's surface. And due to the rocket equation, the amount of fuel and the cost grows exponentially as the vehicle grows larger and the amount of fuel grows larger. One solution to this is to generate fuel from not the Earth's surface in order to reduce this cost. Our goal for this project is to develop a method to obtain resources for long-term deep space operations, not relying on the Earth's surface. Our mission is to generate resources in situ on the lunar surface and transport them to the lunar orbit. This resource would primarily be both fuel in the form of hydrogen and oxygen, and water, both being obtained from ice on the lunar surface. The primary use for lunar orbiting refueling stations such as this would be primarily to serve as a gateway for interplanetary and deep space missions. This fuel station will allow missions that are coming from the Earth's surface to refuel before going into deep space, which would allow them to both have a larger mission envelope, allowing a larger delta V as they can carry more fuel for a smaller vehicle, as well as allowing their missions to perform faster and at a lower cost. In addition, a system such as this could serve cislunar operations, such as missions going to and from the moon back and forth, or long-term lunar operations that would require refueling or water resources, or lunar surface operations that would require liquid water or hydrogen or oxygen. Some organizations that would be interested in a system like this are primarily governmental organizations such as NASA or Roscosmos that would like deep space missions, either manned or scientific missions, as well as private space companies such as ULA, SpaceX, and Blue Origin, which would be interested in more commercial ventures and would also want to deliver payloads to deep space. Or a primary want of a customer would be to actually be able to obtain liquid hydrogen, oxygen, and water. In order to do this, they need a physical interface that works with the customer vehicle, as well as being able to deliver the resources at a certain pressure, rate, with a certain purity, and to deliver a certain amount that a customer would want. These basic requirements are fleshed out. These basic requirements are more fleshed out on this slide, where a more exhaustive list of quantitative numbers that a customer desired. The overall layout of the system is 5 separate systems. The first one being a launch and entry, descent, and landing system, which would transport the other systems from the surface to lunar orbit as well as the lunar surface. A ice retrieval system would be in place in order to be able to extract the ice from the surface and deliver it to an ice processing facility, where it then be melted and converted into liquid water as well as liquid hydrogen and oxygen through hydrolysis. These would then be transferred into a rocket delivery shuttle, which would go from the lunar surface to lunar orbit, where it would be delivered to an orbiting fuel depot. This orbiting fuel depot would then extract all the fuel from the delivery system, store it, and deliver it to customer vehicles as needed, and then the delivery shuttle would then return to the surface to retrieve more fuel. The current concept of operations is having 2 separate launch vehicles. The first one launching the orbiting fuel depot into the lunar orbit, where it would then get checked out and ensure communications are working properly between it and the surface. And then a second launch vehicle would launch also from Cape Canaveral at Kennedy Space Center, which would include a landing system that would deliver the ice retrieval system, the ice processing facility, and the delivery shuttle all to the lunar surface. The ice retrieval system would then get ice and deliver it to the ice processing facility where it'd be processed to water and fuel, which would then be delivered by the delivery shuttle to the orbiting fuel station, which would then deliver it to a customer. Some alternative design considerations were sending an orbiter and landing system in the same launch vehicle. This would benefit the schedule and decrease some logistics required, however, would be quite cost effective and was not seen to be worth the cost. The ice retrieval system was considered to melt the ice and deliver liquid water. This would increase the purity of it and require less transportation of dirt and impurities in the system. However, is more energy intensive, and it was decided that the ice processing facility would have much easier access to the energy needed to melt this than the rover would have. And a possible addition is a customer delivery shuttle, which would actually be able to deliver fuel from the orbiting fuel depot to places, to different lunar orbits or other places or locations that are not in lunar orbit to a customer as needed.
As you can see here on our product lifecycle, we plan to have our orbital fuel depot stocked and available for our first customer delivery in just over 3 years. This achievement will be possible after 19 months of design work and then a year and a half of building, integrating, and testing to prepare us for launch. Following that launch, we are a week and a half away from touching down on the lunar surface, and then another 20 days to delivering our first payload to the orbiting fuel depot. As the operation continues, we will need to replace our shuttles as no rocket engine is yet to be built to sustain that type of usage. And then we will look at expanding our tanks and building upon our rovers, whether that be adding more to our detail or improving upon them. Now we will move on to what the overall system looks like. This is the work breakdown structure of the overall lunar orbiting refueling system. On the left side, we have our level 1 subsystems or our products. And then on the right side, we see our more human-based operations, which we have our mission control, which takes care of our rover and our shuttle and making sure there are no errors there and everything is where it needs to be. Our verification and validation, which will continue to work as we will continue to design and build better rockets or better rovers, what have you. We have our integration team and then our program management team, and they're really are going to be like our customer outreach, making sure our customers and us hold up to our sides of our contracts. Here we have our n-squared diagram showing how each of the level 1 subsystems is interacting with another. As you can see on our first row, and maybe recall from the CONOP that the launch and EDL only will be interacting during the first phase of the operation. Once we hit lunar operations, only this bottom 4x4 will be looked at. From there, we can see that the orbiting fuel depot is really our communication hub and will be keeping up with data from all 3 lunar systems. One of the major feedbacks are going to be between the moon orbit and fuel shuttle and the orbiting fuel shuttle, as each of these need to communicate where one is in relation to the other, as well as what's fuel like on the orbiting fuel depot, how much fuel have we gained on the moon orbit fuel shuttle, to determine delivery timelines and best time to launch based on fuel. Now we want to take a look at how each of these subsystems play a part in the whole of the operation, starting with how we get there in the launch and entry, descent, and landing system. Here we have our launch and EDL requirements. We see our two launch vehicles. Each will go separately. The first launching with at least a payload mass of 2,000 kilograms, as this is going to launch just our fuel depot. And the second will carry our lunar ice retrieval, our processing facility, and our delivery shuttle, which will amount to about 6,000 kilograms. The launch and EDL system can then be broken down into its own subsystems. Here we see the launch system, the EDL system, the communication system, and a payload system, each having its own functions that are part of the entire operation, like the EDL system, which is responsible for delivering the 3 lunar products to the moon.
This is the orbiting field depot system, and these are the requirements. They're based off of interaction between the customer vehicle and the orbiting fuel station. Essentially, this fuel depot orbits around the moon and receives fuel from a delivery shuttle and either stores it or transfers it to a customer vehicle that processes it. It also produces enough energy to sustain fuel transfer and communication. So this is the ice processing facility system. These requirements are based from being able to store the fuel and process the ice that it receives. Essentially, this facility, which is powered by solar panels, receives ice from the lunar rover and processes it into fuel with electrolysis. The fuel is either stored or transferred to the lunar shuttle. Moving on, this is the Moon Orbit Fuel Shuttle, and these are its requirements. And these requirements are based from being able to carry enough fuel and deliver them to the orbiting depot. This is the functional breakdown structure for the system. Essentially, this shuttle receives and stores fuel from the ice processing facility, launches from the moon, and delivers them to the depot. The shuttle then descends to lunar surface to pick up more fuel. Additionally, the shuttle is able to be connected to the facility for recharging.
Next, we're going to be talking about the ice retrieval system. This is a subsystem that works a little bit in the background of the main systems that the customer would be interested in, but this is something that's absolutely necessary to the production of fuel and delivering all of the customer requirements asked for at the beginning of this presentation. The first thing we're going to do is define the overall requirements for the retrieval system. And so what this basically looks like is something that moves across the lunar surface and gathers ice. And as you can see, we've set requirements asking for specific ice extraction rates, speeds, and various power and data transmission requirements in order to keep the operation underway and to provide the customer with an efficient and productive cycle. Our functional breakdown structure showing the 5 different subsystems that we've defined just for the retrieval system. These include mobility, which is how we're going to move the rover across the lunar surface, the power system, which is how we maintain the operation of it, whether that be through extracting the ice or the mobility, and the communication system, and how we make sure that mission control is able to keep track of this subsystem. Here you're looking at the n-squared diagram just for the retrieval system. If you look at the top left and the bottom right, you have the power subsystem and the mobility subsystem. And I think the interface between these two systems is one that's interesting to look at. If you look in the top right, you see that the power subsystem is providing the mobility subsystem with the electricity to drive it. But a less thought of interface would be where the mobility subsystem is sending the electricity consumption rate back to the power subsystem, which can be seen in the bottom left of the diagram. Now we're just going to show some of the requirements that we developed for the retrieval subsystems, the even smaller level subsystems. So this is just extraction, which is just the system that would be pulling the ice out from under the lunar surface. We set things such as operating limits and things like that to make sure that it's always able to gather ice and that it has a reasonable longevity, such that we are not having to run frequent missions to the moon. The mobility subsystem sets things such as maximum acceleration so that the traction team is able to define exactly what conditions the rover needs to keep traction under, and defines other various power requirements about consumption rates and things of that sort. The output subsystem is a subsystem designed specifically for maintaining the interface between the processing facility and the retrieval system. This is just to make sure that the transfer of ice from the retrieval to the processing is as smooth as possible. The electrical power subsystem is one that's specifically for keeping track of battery health and maintaining power input as well as power output to keep the retrieval system for running for a long time. And finally, the communication subsystem, one that is very important for mission control to maintain the rover and to make sure that it's operating correctly at all times, and also such that all the other subsystems within our system are operating efficiently and understand what to expect out of this specific part of the subsystem.